Today, we will deal with cellular-automata-based simulation of dynamics, recrystallization, and statistical analysis of resulting grain growth. So, going from group to crystals is somehow, I wouldn't say natural, but a logical step. And I invite the speakers to make their presentation.
Yeah. Hello, everyone. Is my voice clear?
Yes, maybe if you can just add a little bit of volume to your. Otherwise, it will be all right. Don't worry.
Okay, sir.
Yes.
I will start presenting my screen. Yeah, actually, the option for sharing screen.
Slow down.
Okay. So, is my screen visible?
Yes, good. So please go ahead, Subramanian.
Yeah, okay. So once again, hello everyone. So this is Subramanian RS, a third-year undergraduate student in the Department of Metallurgical and Materials Engineering from National Institute of Technology, Trichy, India. So this talk will be focused on cellular-automata simulation of dynamic recrystallization and statistical analysis of resulting grain growth. So the other two contributors for this work are Ramadev Shree and Prince Gideon sir. So this is our first attempt in using the tool of Cellular-automata in understanding the phenomena in our domain of material science. So as most of you might not be familiar with our field of material science, I would like to spend a considerable amount of time with a introduction to the keywords in our field so that it will be easy to understand in the later part of the talk. So let's enter into the world of material science. Starting with a curiosity of how our daily kitchen utensils, which is of various shapes, are getting manufactured. Let's travel from industry to kitchen. So we have a block of a material, let's say a stainless steel. So it is being made into various desired shape utensils. So using operations which we generally term as forming operations, here we kind of applying pressure and forces to get our desired shape. So macroscopically with naked eye, what we observe is the direct shape change. So now a natural question arises, what about the changes in the internal of a material, like at the very smaller length scales? So let's hop into the world of smaller length scales. So while going into the length scale of the order of 10 power minus 6 meter, so we observe kind of structure that you can see in the left bottom image. So this kind of structure we usually observe using the microstructure, whose images you can also see in the slide. So they use the principle of optics and electron beams to make us view these kind of structures. So such kind of structure at this length scale is generally termed as microstructure. So as we all familiar, like in our country of India, we have so many states with every state oriented towards a particular culture and practices. So in the similar line, in the microstructure, we have various regions where the orientation of atoms will be in a particular direction. So such regions we generally term as grains. And even in a country, we have borders separating one state from the another. In the similar way, we have grain boundaries which separate one grain from the another. So such structure in which we can find more than one grain is generally termed as polycrystalline microstructure. So then here also a question normally arises, why do we really have to consider the changes happening in such a smaller length scales? So let's find the answer with an example. So here in the left corner, we have two familiar Indian dishes As you all know, both of which are made from same basic ingredient rava, but the way in which it got cooked influences to some extent the way it looks, like how we feel while touching, and in turn it influences how it actually tastes. So in the similar way, the process which a material undergoes will determine what microstructure it will have, and again in turn the microstructure will reveal what the properties we can observe macroscopically. So in the center we have a set of images where the above one has large number of grains than the below one. So they too exhibit different macroscopic properties such as strengths. So from this it is clear that the property revealed is the indication of the microstructure internally present. So it is really important to have our consideration on studying these microstructures. So now that we have seen why microstructure needs our consideration, we will look into what microstructural changes really happen during our operation of converting block to a kitchen utensil. So two significant changes is observed here. First of which is the reduction in the average size of grains, and second is the introduction of some sort of defects which we term as dislocation into the system. So for the first microstructural change, which is the reduction in grain size. So as the grain size comes down, we have relatively more number of grains into the system. Hence, there will be more number of grain boundaries. So in the material science, the movement of the defects called as dislocation primarily macroscopically define the plastic deformation or simply shape change. So how these dislocation move will determine my shape change. So as these have large number of boundaries, there will be more number of interruption for these dislocations while movement. So hence it will affect the further shape change or further deformation. So as you can see in the images here, the right one has hurdles placed very close to each other, so that it will be difficult for a person to cross this hurdle rather than the one in the left. So in the similar way, the dislocation will find difficult to move in such a system. So moving on to the next slide. So the second changes which we saw is increase in the number of defects called dislocation. We quantify those number in terms of a term called the dislocation density. So here you can see like the same room, as more number of people come into the same room, the movement between them will also be less. The mobility will be less. So in the similar case, as the number of dislocation increases, there will be difficult in their movement, and hence there will be difficult in our shape change. Hence, it is detrimental to the further deformation. So as we saw, so hence for us to proceed with the shape change without damaging the material, there must be a phenomena which can reverse the above changes so that it will be really helpful in our process. Such phenomena generally we call as recrystallization. So one of the problems we face is an increase in the number of defects. So this recrystallization involves the appearance or nucleation and growth of defect-free grains. Hence, it helps us in our further shape change process. So there are generally two types of recrystallization. We call static recrystallization and dynamic recrystallization. So in static recrystallization, the process temperature involved is generally low. So once a particular shape is arrived, after that it is heated to a temperature so that these circulate and grow. But in dynamic recrystallization, the temperature involved in the process itself is high, so the nucleation and growth free defects happen simultaneously with the process. So as most industry process prefer dynamic recrystallization over static recrystallization because of its efficiency, and also it is difficult to experimentally have a look at the microstructural changes at such a high temperature process. So here there comes a need for a theoretical model to address this behavior, as dynamic recrystallization have an extra burden on its top. So here comes the Cellular-automata into the scene. So as most of you might be familiar with Cellular-automata, here space and time is discretized and specific states are assigned to every cell, and it is changed based on the transition rules we apply. And these transition rules we apply will be kind of similar to one that we observe in the real phenomena. So now coming to the model description, here you can see the schematic working of our model. So initially we have a homogeneous domain, and when it goes through the static recrystallization model so as to get a polycrystalline microstructure, which with it can actually start to work with dynamic recrystallization. Then again it is fed into the dynamic recrystallization model, giving us the result of a final microstructure. So for this study, we have used the model developed by Dr. Krog to understand the phenomena. So here you can see the references given here. So yeah, exclusive explanation can be found in these references. So now moving on to the question, what's exactly happening behind those yellow boxes? So first of all, taking the static recrystallization model box. So initially we have a homogeneous domain to start work with. So then we introduce several nuclei into the domain, so which has a state of a recrystallized state. Then they are allowed to grow, which means that unrecrystallized state will transform to recrystallized if one of its neighbor is already in recrystallized state. So in this way, we are allowing the introduced nuclei, randomly distributed nuclei, to grow. So hence it eventually starts to grow. And once it grows, it will start impinging on one another, and it stops further grain growth. Growth of that grain is stopped further. So we finally obtain a polycrystalline microstructure with which we can start our actual focus on dynamic recrystallization. So now we are feeding this to dynamic recrystallization model. So each cell in the polycrystalline microstructure we associated with a vector which essentially contains three components, one of which is orientation, which essentially tell us to which grain the cell actually belongs to, and dislocation density, as we saw earlier, it quantifies the number of defects present, and waiting time. This is the parameter which generally means like how much time it has to wait until it becomes recrystallized. So this parameter defines that. And some of the input parameters that are asked in the model. So first three, as you can see in the right side, first three are our essential components of our vector. And in the left image, in the model, we'll be giving these inputs so as to get the polycrystalline microstructure, and also proceeding with the further processes. So here we mention how many nuclei initially we are introducing, and the critical value of dislocation density, and further inputs figure, which we'll see in the later part. So now what is actually meant by a cell in grain boundary? So we saw earlier that the grain boundary is a region separating two grains. So here you can see the red line actually separates the yellow region from that of a blue region. So a cell C, as you can see, is adjacent to this line. So hence it can be called as a cell which is present in grain boundary. So now moving on to the how the model actually processes the things. So for every cell C, you will see several criteria that has to be met. So first of all, to checking whether the cell is found in the grain boundary region, and then if the difference in dislocation density of the cell and its neighbor exceeds a critical value, and then checking whether the waiting time associated with the cell is actually 0, and whether it is in good shape, which essentially means that the new configuration of the boundary should not have narrow hollows so that it contradicts the one we observe in the real life. So these criteria are checked, and we introduce a probability factor of 0.5. So the reason behind introducing this is to protect the shape of grain so that it resembles the one we observe in the real life. So if these all criteria is met, then recrystallization even happen for that cell, which essentially means that the dislocation component will be set to 0, which means the recrystallized one is defect free, and the waiting time is set to the maximum possible value, and the orientation of the cell is set to that of the orientation of the neighbor, which means that the cell with a lower dislocation density consumes the one with the higher dislocation density. So if there is no recrystallization event happening in the cell, then it essentially means that any of these criteria has not been met. So then this happens, like the waiting time of each cell is reduced by 1, and the dislocation density is increased by the rate of increase, which we generally mention in the input parameters of the model. So once it is checked, it is the event other than happening recrystallization event. So other than these two, we have a random nucleation happening at the grain boundary cell. So with it, as it is random, we associate a probability factor with it, and it is checked that whether that cell has dislocation density which is greater than equal to a critical value for nucleation, which we will also mention in the input parameters. So if these three get satisfied, then nucleation happens at the grain boundaries, which means that the new formed grain has a orientation as random, and dislocation density is set to 0, which means they are defect free, and waiting time is set to maximum waiting time. So all these eventually end up in the end of operation for that particular step. In this way, it is continued for several time steps to have an idea of its evolution. So now here you can see, as we saw in the nucleation part, several nuclei are start appearing on the grain boundaries. So then they eventually starts to grow, and we can see the subsequent growth during the dynamic recrystallization process. So now coming to the domain setup we had. So in this we had 2-dimensional setup, and the lattice size they have chosen is 256 cross 256, and periodic boundary condition is employed here, and the neighborhood which is employed is Moore neighborhood, which essentially contains 9 neighbors including the cell under consideration. And values for input, we have the initial embryos as 250, and then the critical value for dislocation density is 255, and that for nucleation we have is 50. These values we used for our further understanding of the behavior. So now we moving on to the part of the results we got and discussion about the results. So now, first of all, starting with what a grain growth is. So the grain, essentially a microstructure has grain boundaries. So as we saw earlier, it is a area of mismatch between two grains. Hence, it is usually associated with high energy. So a system naturally wants to get rid of this. So grain growth phenomena will come handy in that. So conventionally, what grain growth is? The growth of large sized grain at the expense of smaller grains, so that we'll have a reduction in the overall area of grain boundaries. So, but while we see the dynamic recrystallization grain growth, as we saw, the growth of grain with lower dislocation density will grow at the expense of the one with higher dislocation density, so that the effective number of dislocation will come down and help in our deformation process. So here in the left side, we have mean grain size versus number of time step graph. So here you can see there is a progressive decrease in the mean grain size. So in conventional grain growth, there will be, we can see an increase in grain growth, but here you can see only a progressive increase in grain growth. So question arises whether there is no grain growth at all in dynamic recrystallization. But when we closely zoom in between a particular time step, we can see a subplot within this plot, where you can see there is an increase and decrease like happening one after the other, which is usually a rather, which is not familiar trend. So we are trying to plot number of grains versus time step. So in this we can see the similar structure of increase and decrease. So in our process, we had a nucleation process, which means introduction of new grains. So hence this accounts for the increase in the number of grains, and the grain growth, the growth of the grain with lower dislocation density into the higher one, which signifies the decrease in the number of grains. So this is the reason behind the increase and decrease in number of grains. So it's correspondingly we can see the decrease and increase in the mean grain size graph. So moving on to the next plot, here the same graph we have taken, and events within those. Here we have labeled from 1 to 3 and 4, 5, 6. So here you can see the increase, like we consider the increase part of the mean grain size. We have 6 subplots within that. And this resembles the one we usually observe in a conventional grain growth. So for comparing the kinetics of conventional grain growth and the one with dynamic recrystallization, we use these sub-events. So while regression approach we have used to identify the order of evolution. So as you can see, the third order of evolution has the minimal error. So it suits most the grain growth kinetics of the dynamic recrystallization, which is contrary to the conventional one where we observe second order power law in this evolution. So it is evident from this diagram that in addition to the degree of fluctuation, the kinetics exhibited by the individual event steadily decreases as the dynamic recrystallization starts to proceed. So despite of all of this, all the growth events invariably they follow the third order growth law. So here we come to the conclusion. So as we saw, the rate of growth event gradually decreases as the dynamic recrystallization proceeds. And after this, statistically rigorous study will follow, where we can employ material-specific values of critical dislocation and nucleus density, so as to resemble the actual physical phenomena. So here we would like to express our sincere gratitude to Dr. Sukandara sir and Dr. Kamalika ma'am, who were really helpful in making us understand this area of cellular automata. So in future, we are also hoping to develop our own cellular automata model in explaining a phenomena called stress corrosion cracking. So we are hoping to develop our own model instead of using the derived one. So yeah, this is the end of the talk. Thank you for listening. Now opening to any questions.
So thank you very much, Subramanian. So time for questions now.
I have a question for Subramanian.
Yes, please.
Subramanian, so what you have done, that is based on two-dimensional grid, right?
Yes, a two-dimensional set.
Yeah, yes. And your rule is a bit complicated, what I've understood.
Yes, sir. Several conditions are being made so as to resemble.
Okay. I mean, is it possible to do this thing, on one-dimensional grid?
One-dimensional grid. So actually, it was like maybe as our micrographs which we use in our material science are mostly the two-dimensional images. Yeah. So this two-dimensional setup will better explain the evolution of microstructure, so that it will be easy for us to understand. So that's the reason maybe this two-dimensional has been chosen.
Okay, so it's not possible, right? Or you didn't think it?
Actually, we haven't yet tried the one-dimensional. As we have the resemblance in the microstructure, we stick to this two-dimensional.
Okay, thank you.
Thank you, sir.
Good. Are there other questions?
Yes, Subramanian, I have one question. And your first of all, thanks for your nice presentation. You have mentioned that you have used periodic boundary CA. Have you tried with other boundaries? Would it be suitable for your designs? Why you are basically choosing periodic boundary CA?
Okay, so actually we have the lattice size as 256 cross 256. So in general, in the material science domain itself, we consider like small portion of that area and then periodically repeating so that we get the entire structure. So here, as a resemblance to it, periodic boundary condition helped in the evolution of the grain. So as we don't have a constricted thing over here. So as it is continuous in a periodic manner, so we have choose like homogeneous. We consider a homogeneous system so that it repeats periodically, so that it will be resembling the one in the physical understanding.
Okay. Anyways, if other participants have any questions, please.
I have one suggestion.
Okay,
All, like you were saying, Subramanian, that all these are specific to your application, your metallurgical application, your images over that you have processed, and according to that you have designed. So my suggestion is, why not you also explore the other aspects, other theoretical aspects of the design, and maybe you can get some results which is not only applicable for your metallurgical domain, but in some other domains also, because it feels like there are some like lots of possibilities. Your
okay,
rule
ma'am,
is,
sure.
yeah, your rule is little bit complicated, but like you are showing some boundaries, in between boundaries, within the cells there are some boundaries for which you are designing something. So for that also you have to decide the rule accordingly, and you are using periodic boundary. So maybe if you change the boundary condition, then something will evolve. If you change the rule, something will evolve on the same model. So why not you explore that theoretical aspects also?
Yes, ma'am, sure. Like, we'll definitely look into it.
Yeah, and thank you for the nice presentation.
Thank you.
Good. Are there other questions? Personally, I would like to ask a question about the possibility to consider a probabilistic setting for your study. Maybe you have studied Ising models, for example, which are defined with a given probability for transitions. So did you consider, let's say, adding more probabilistic flavor to this model?
Yes, sir. Actually, this probabilities initially in that model description, these probabilities were introduced so as like initially without probability distribution. While seeing the evolution, this is more or less getting dependent on the shape of the cells and something. So it is not having the shape of globular shape, which is generally we observe in the material science. So that probability has been introduced and also to accommodate the various like the natural thing we observe, like in the grain boundaries, not all grain boundaries will nucleate. So for that factor, we have introduced a new probability there so as to get a reasonable approximation to our actual process phenomenon. So that's the reason why probability has been fixed here. Without probabilities in the description given by Dr. Kroc, it was given that there was not the shape of the grain was not suitable to one we observe. So hence this factor has to be reduced so as to get the meaningful results from this model.
Okay, thank you.
Thanks.